All right. So there's a bunch of stuff you guys will be learning, so don't freak out. All right. So that leaves us with moving on to something a little bit different. We're going to talk about engines. All right. So now we're going to talk about compression. Compression ratio. So we're going to get into some stuff like this. Well, I will define it for you. The compression ratio. You know, when I say ratio, it should be the difference between two things. Is the ratio of the volume, not how loud it is, but how much it holds, volume of the cylinder at bottom dead center, that's a D, bottom dead center, I'll just do this, bottom dead center to top dead center. So it is the difference of how much liquid, even though we put liquid in there, it's just easier to say liquid, how much liquid the cylinder holds when the piston's all the way at the bottom versus how much it holds at the top. And a compression ratio is going to be a big deal to you as an aircraft mechanic. You don't get to decide what it is, but it kind of tells you a little bit about the construction and what's going on with it, what kind of fuels it can use. So let me see. Here we go. Example, if a cylinder contains 50 cubic inches of, let's say, air at bottom dead center, and 10 cubic inches, all inches cubed, that's the same thing, inches cubed is cubic inches, inches cubed at top dead center, the compression ratio is 50 to 10. Well, we don't say 50 to 10. You try and bring it down to 1 if at all possible. So if I divided both of these things by 10, 50 divided by 10 and 10 divided by 10, I would get a ratio of 5 to 1. All right. Increasing the compression ratio is sort of a good thing. It increases power and efficiency. But there's a trade-off. If you raise the compression ratio too high, the fuel can't handle it. So the fuel, well, there's two things that are really a limiting factor. One is just the physical attributes of the engine. If the compression ratio is too high, you'll actually just blow the head right off, and that's bad. So you got to, diesels have very high compression ratios. If you tried to run that same compression ratio in a car or even in one of these airplanes, you would have what I would say is a dynamic disassembly. That means it came apart. And then fuel. Fuel plays a big part in that too. When the compression ratio gets too high, the fuel doesn't burn, it detonates. So we're going to talk a lot about fuels in the next class, but that's why when you go to the store and you have a choice between grades of fuel, it is not bad gas versus good gas. It's all the same gas. It's low octane versus high octane. So, there's those people who say, well, it's just my baby and I love my car, so every third tank I put in the 91 octane. And it's like, you're just like, oh, thank you, 91 octane. It doesn't work. What's that?
And they drive a Corolla or something.
Yeah, it's exactly it. Why do you drive a Corolla? Okay. So, yeah, Steve?
So like when people like to buy new aircraft, they say, oh, you got to do the cylinder compression checks and all that. But you set those, right? Those don't change.
Oh no, that's totally different. That is totally
like
different.
rings in your head.
Yeah, that's leakages. So okay, so increasing the compression ratio, power efficiency. Oh, so where I was going with the car. So if you look at whatever car you have, the car is going to tell you what the octane rating is. So like if you have a Corolla, is that what we're going to pick on today? So if you have a Corolla, and because you're smart and you didn't buy something that took high octane. Who has a regular running octane Nissan kind of, all right, because you're smart, and you can buy the cheaper gas because it's cheaper to make because it doesn't have the high octane, or they just know that you're a chump and you'll pay more for gas probably. So you get away with that. Now who has to run the high octane in here?
You, Corvette.
Corvette, all Mercedes, BMW.
Cadillacs, even some of them.
I think some Cadillacs. Although I think in the manual says you can pick. I don't know about that.
Some of the Volkswagens.
Oh yeah, and some of the new Volkswagens because they're basically, Volkswagen is like like an Audi, which is also Bugatti now, right?
So does that
Okay.
mean your Mercedes is high compression?
It's very high compression. So it's so they do that because it gives me more power and efficiency, but that comes at a cost. The gas is higher, so that's a whole nother lecture. So when we look at aircraft, if we go back in time, when I was a young man, we had a choice of fuel. You could get the 80, 87, or the 100 octane. Well, you go back further, there's a lot more fuels. We'll talk about all those. But so I'd pull up to the airport and say, hey, what do you want? I'll take 80, 87. And some guys, no, I'll take 100. You actually had to pick the right gas. Well, then they got rid of the 8087, and I'll explain why they have two designators. It's 80/87. And now there's just the 100 low lead, which is a misnomer because 100 low lead has an extreme amount of lead to it. So that we just call it low lead so that the environmentalists go, it's low lead, right? That's low lead, yeah. Compared to the stuff we used to use. But if you're watching this on YouTube, I'm just joking. So it's really just low lead. Nobody watches this on YouTube, so I don't have to worry about that. Power and efficiency. Ooh, power and efficiency. Explanation point. There we go. Okay, so compression ratio too high causes detonation. Causes detonation of the fuel.
Pinging.
That is pinging. Detonation and pinging are synonymous terms. We just don't say pinging in aviation, but it's the exact same thing. And you ever heard your car ping?
Yep.
Okay, so your car has a sensor in it called a knock sensor, and it hears that because it listens, and it detunes it, so it'll change the timing, and it'll pull things back so it doesn't disintegrate. You can't hear that in an aircraft because of propeller noise. So it just what you hear is the dynamic disassembly or the propeller stopping, and then
The cylinder depart light.
that's right. This comes on. Well, it's actually the piston melt light comes on. Pressure ratio causes detonation of the fuel. And then, just so you remember, detonation. And I'll put pinging here. P-I-N-G-I. Pinging, so you get the idea. Oh, it's right there in my notes. Is like hitting the piston with a big hammer. It's even worse than that because it melts it. It has localized hot spots and causes engine failure. It's a very serious problem. You do not want that. Because if you're talking about an engine that's $20,000, $30,000 and you just pinged it to pieces, that's really sad.
So what exactly is detonation? Is that there's no combustion?
No, it's the opposite. So in normal fuel combustion, it burns. It is actually a burning that if you slowed it down, you'd watch it light off and do an appropriate burn. Okay, detonation is an explosion. It's just a sudden bang. It's like, well, you don't want that. You want, I don't know, burn and push versus explosion. Explosion is detonation.
Is that why it's important to jet things to altitude?
Well, we don't jet things in aviation at all. because we have a mixture control that the pilot can actually operate. So everything is jetted appropriately for sea level. Everything is. Everything works at sea level, and then you manually lean it appropriately as you go. The exception to that is you can set the idle mixture. So higher compression ratio needs, can I just put CR? Higher compression ratio. Engines need higher octane fuel. And again, we're going to talk fuel like for an entire week straight in next class. So, anybody remember what the compression ratio of the Lycoming O290D is?
6.5 to 1.
Wow, good job, because it says it.
In the magazine.
And on the bottom of your pistons. So typical compression ratio for aircraft is about 7 to 1. Lycoming states that low compression is 6.5 to 1 to 7.9 to 1. High compression they define that as 8 to 1 or higher. 8 to 1 or higher. And the overall range that I could come up with Lycoming is 6.5 to 1 at the low end, all the way up to 10 to 1. Up to 10 to 1. Interesting thing is most turbocharged engines run lower compression ratio.
Because of the forced induction.
A couple reasons we can get into a turbocharger, but yeah, number one, you're adding some heat in there, which I think might have play a part. But two, because you're maintaining a constant boost, or it's actually boosting it in some cases, so they lower the compression ratio. All right, where am I here? A, B, C, D, E, F. I don't think we need to talk about. Remember, there's a difference between compression ratio and boost pressure. One is just the ratio, and the other has to do with absolute pressure. Well, maybe we can do that. So, okay, remember. I like it when I put remember, and it's something I never talked about. Like, you should know this, but you don't have to. Remember, okay, there is a difference between compression ratio, CR, compression ratio, and put boost pressure, which can also, I can also say manifold pressure. So in aircraft, especially if you have a constant speed propeller or a turbocharged engine, and by the way, if you have a turbocharged, you can bet you'd have a constant speed. Because it wouldn't make sense to have a fixed pitch if you're going to put a turbocharger on. But anyway, so as a pilot or somebody flying a controllable pitch propeller, you add another knob. So not only do you have the throttle, which is the same as your gas pedal, but you also add a blue knob which controls the pitch of the propeller. So at one point, we'll talk about this more, it's going to be confusing. At one point while you're flying, the throttle no longer really controls RPM. Like in your car, the more you mash down on the throttle, the higher your RPM goes, right? But then it switches gears and goes down, which is almost the same as a propeller. So you get to a point where the throttle, actually, it still controls the throttle plate, which then has a direct correlation to how much pressure is being allowed into the engine. And it's just manifold pressure, which it's because it's a manifold, so we call it manifold pressure, intake manifold pressure. So, and then the propeller will control your RPM. So you can speed up or slow down based upon the pitch of the propeller. So when we talk about compression ratio, remember it's the volume of two things. How can I change that ratio? There you go. Get a different size piston. That's exactly it. Get a different piston. So you got to take the whole engine apart and change it apart. Okay. So if I want to change compression ratio, I have to buy new parts. Yes. Okay. So like that's exactly. There's a Lycoming makes like their 0320 engine. The 0320. So how many cubic inch? 320 came in two versions, 150 and 160 horsepower. What was the difference in part? What was the one thing they changed to the difference? Just the piston. It's the only part they had to change. So there's an STC out there, which you could get the Lycoming, it was the A or the E versions, like 0320A, 0320E was the low compression, I think, and that was 150 horse. You can get by an STC if you owned that engine. You just took the cylinder off, changed the piston, put it back on basically, and boom, you have 160 horsepower. All right, so because you changed what? Compression ratio. Okay, so manifold pressure, how do I change manifold pressure?
Put a bigger turbo.
Well, you're right. That's something a pilot controls. So do you have to buy anything? It's the pilot. All right, so the difference between compression ratio and booster or manifold pressure. So one is a ratio, we have to change parts, and the other one is just something that happens as part of flying and operating an engine. All right. I don't think we need to write this. And so in order to find out the compression ratio, you have to know two things. What do you have to know? Volume at the top, volume at the bottom. All right. Okay, then we get into displacement, which is closely tied to that. Technically, it is the amount of liquid a cylinder displaces, which means pushes out, displaces during one stroke. Just one stroke. Starts at the bottom. How much did you push it out? All right. And you are going to have to do maths, and you're going to have to figure out displacement of engines. There are many FAA questions about this, and there's no reason why you can't just breeze through this. All right. Let's see. I don't think I'm going to write that. I'm just going to do it this way. Well, okay, so to find the displacement, first you're going to find displacement of an engine, One, find the area of the piston. In other words, how many how many square inches are on the face of the piston? So how many little inches would fit on there? And how do we find the square inches of a piston? Okay, it's area equals pi times the radius square. And remember, we have to use the please excuse my dear Aunt Sally. We have to do it in the right order. And the order, please excuse my dear. We came up with a new one, didn't we? 309?
Yeah.
Please excuse my drunken, I don't know, drunk ass, I don't know. Please, no, it didn't say that. Please excuse my dear Aunt Sally. Okay, because MD and AS are equivalent. I wrote it like that. So it's parentheses, exponents, multiplication, division, then addition, subtraction. So are there parentheses? No, but there's an exponent, the r squared. So we're going to cover that. So find the area of the piston. All right, then multiply times the I'm going to write out times the stroke, and then multiply times, because what you did is you just found the cubic displacement of one cylinder. That's all you did. Find the area of the piston, multiply by the stroke, boom! That was the displacement of the cylinder. But what are we trying to find? Displacement of the engine. So multiply times the number of cylinders. Number of cylinders. I have to scroll up. There we go, number of cylinders. So let's try one. All right, so we have 5.25 inch bore. It is a 4-inch stroke, and it is a 6-cylinder engine. Okay, so the first thing we need to realize is I said the area is the pi times the radius squared. We look at a cylinder, or a circle I should say, we need to remember that this is the radius. Red is radius. And this is the diameter. And they should be in the middle, sorry. Diameter. And diameter is synonymous, means the same thing in engines as the bore. All right. So first thing we got to do is we have to get this area equals pi r squared into something that makes sense to us. So it's the area equals, I'll write it here, pi times the radius squared, but I gave it to you in the bore. So how do I find the radius off of that? All right. I suppose I could write area equals pi times bore divided by 2 squared, something like that. But I hate doing that kind of stuff. So that's like radius squared. And you got to remember, let's change it to radius. So what is the radius here? Oops. Area equals pi. I'll do it slowly. Times the radius. What's my radius? 2.25 squared. Okay, so I got that much down. What's my next step? Well, you're the one yelling out on my calculator. I have to go to my calculator. What is the radius? It's 5.25 divided by 2, which is 2.5. What is it? 2.625 squared. I'm going to get my calculator. Talk amongst yourselves. Okay, once I've gotten around that little trick and remembered radius and diameter, because you guys are going to mess up on that, right? Somebody's going to mess up. All right, stay with me. Ready? Got it? Okay, so we did 5.25 divided by 2, right? 5.25 divided by 2 equals 2.625. Now we got to square that. The very next thing we do, so we're going to hit the x square button right here. X squared, and we get answer times square equals 6.89. Okay, so that is area equals pi times 6.89. That's times. Now all I have to do is hit the pi button, which is above the caret. So times pi equals, we got what, 21? Area equals 21.647. I'm going to round to the second decimal place. I'm going to round here, so that'll be area equals 21.65. Now what? Times the stroke. So my stroke is 4 inches, so I'm going to times 4 equals, I get 86.5, which is 86.59. We can round up to 86.6. I'm just going to leave it in my calculator anyway, the way it is. And now I have to multiply it by times 6. Times 6 equals, and you should get 519.54. What do I have right here? That's an 0520 at least. Continental 520. Because you're going to round up to the nearest 10, right? So round to the nearest. So got 0520. Everybody clear on that one?
No.
No. Thank you for saying that. Okay.
Where did you get 2.625?
2.62. Right here?
Yeah.
Okay, that's where I was worried I was going to lose somebody. Let me go back up a little bit. It is area times the radius squared. Okay? What is the radius?
The center.
The radius goes from here to here. That's the radius. Okay? The blue is the bore, or the diameter. So I told you that it has a 5.25 inch bore. Is the bore the diameter or is it the radius?
The bore. Diameter.
Right. And what does the formula ask you to use?
The radius.
So how do I get the radius out of that?
So you divided the bore.
Mm-hmm.
Right? Kind of, you divided by 2?
Yeah. Because look, it's just, yeah, I'm just missing this part right here, right? If I did it all the way across, that'd be the diameter. If I did it all the way across, this is diameter, that's diameter,
Yes.
radius. Diameter, radius. Bore, radius. Bore, radius. So when they said bore, it's like diameter. They should have said that, but they don't. They say bore, because that's what we call it in engines.
Okay.
So you have to divide it by 2.
Oh, okay. That makes sense.
Now you might, like I said, you might want to write the formula a little bit different, so that maybe you remember that. I just think it gets more complicated at that point. All right, so what I'm going to do on that one, because it would just be redundant after that. So you just have to remember, convert the bore into the radius. That's the trick. All right, let's talk about horsepower. Horsepower, or as a guy I used to work with, he would call it horse pressure. How much horse pressure that thing got? So, horsepower is all about work. Work. And what is the definition of work? It is not. Work equals force times distance. I remember having lunch with my son when he was at school, and we were with his buddy in the cafeteria at the school. And my son went to go take his tray full of the dishes to the little place where you turn them in. And his buddy says, "Dude, take my dish. It's no extra work for you." I said, of course, you have to know my son. That is literally the definition of work. It is force times distance. So you have literally. So he was not a math. My son is a math major. The other guy wasn't. So. Okay, so it's work. Yes. Okay. So so we have work. That's our definition. Well, the definition there. And then we have to talk about. So before we keep moving on from that one, we have to talk about measurements. Measurements. Well, first one is foot pound. Foot pound. Foot pound. It is 1 pound. 1 pound. Of mass, if I want to get technical, of mass raised 1 foot. A foot pound is not that torque measure like that. 1 foot pound. All right, then we come back around to horsepower. Horsepower. All right, where do we get the term horsepower from? I think, did I tell this story maybe in 309? I feel like I've told it recently.
You did last semester.
All right, so horsepower. It's actually, if I remember correctly, it was the guy who made the steam engine who was, I just had the name. I know it's. Anyway, the guy wants to sell a steam engine. So, and I forget who it was. Sorry if he's listening on YouTube. So he wants to sell this steam engine, but he can't. He takes it to the mining operation, and so he's trying to say, use my steam engine because it's more efficient and powerful than this many horses, you know, or it can do the work of that. And so they didn't want to buy it because they couldn't equate it. So what he did is, and I wish I remember his name, but I don't.
Thomas Savory.
Huh?
Thomas Savory.
Savory?
I believe that's how you pronounce it.
No, I was thinking of somebody else.
What?
That's it, James Watt.
Oh.
Okay, so thank you. So he figures out that how much work his steam engine will do, but he uses a workhorse, but it's very specific. It is an English workhorse. An English workhorse.
Those are big horses.
I thought it had something to do with being lazy around tea time or something. All right, so he figures out an English workhorse could work. How much work could an English workhorse work if an English horse? At a rate of, and this is again not during tea time, 550 feet-pounds per second. Well, how much is that per minute? Times 60. 33,000. You're going to see this number a lot in formulas that we're going to do. Like, why divide by 33,000? I want you to remember this. It goes back to the English workhorse, 550 feet pounds per second, or 300,000 feet pounds lbs per minute. Per minute. And that's where this is going to come from. All right, so I'm gonna circle back around, talk about these a little bit later. That's foot-pound, horsepower. So anyway, he figured out, and then I think he sold a bunch of his steam engines because he could at that point. So we have different types of horsepower. And the FA does ask you about these different types of horsepower. Oh, I'm out of space. All right, everybody got this stuff?
That's 10 pages of typing.
I know, my hand hurts. All right, edit, clear, don't say wait. Okay. It's all right, it's already typed out right here. I can just show you this. Yep. All right, we have different types of horsepower. Types of horsepower. Types of horsepower. What kind of horse? All right. Who cares? Indicated horsepower. Indicated horsepower. Indicated horsepower is basically the theoretical horsepower that is created inside of the cylinders. It's something that I can come up with math. So I do math, I'm going to get indicated horsepower. And we're going to work through something in just a little bit. So it's power produced in the cylinders without reference, means I don't care, not counting it, to friction loss. What is friction loss? It's the horsepower of loss through friction. The rings scraping the side of the cylinder walls is a great place to start with friction loss. Without reference to friction loss in the engine. So in other words, it is totally theoretical. It's not actual. It's like you wish kind of horsepower. It's probably the way Volkswagen computes their horsepower. I'm just picking on them because of the smoke. All right, so it uses, I wrote utilizes, but the mean, what is mean?
Average.
That's what I am to you in the lab. Mean effective means average. Mean effective cylinder pressure. So it's the average cylinder pressure. And we talked yesterday about the fact that this pressure gauge goes all over the place, right? So sometimes it's low, sometimes it's high. So it's going to use the mean effective cylinder pressure. Where would I get the mean effective cylinder pressure? Somebody has to give it to you. You can't put a gauge in there and try and figure it out. Don't even try. Well, maybe you can try. I don't care. That is the average pressure in the cylinder. Pressure in the cylinder during the power stroke. Don't care about it the rest of the time because it's power we're after. So I don't care what the pressure is during the exhaust stroke because I'm trying to determine power. All right, so it is done with the calculation. I would tell you, why would you need to know something this weird? Actually, once you know the calculation and the things that go into horsepower, for me, it's like certain things just clicked on. I'm like, oh, I get it. That makes perfect sense now. And I just hadn't thought about it. But it's a calculation is called Planck. P-L-A-N-K, where P is the pressure. It's pressure. I'll just put pressure, which is really the indicated mean pressure of the cylinder during the power stroke, so indicated mean pressure. L is length. Length, and it's actually what? The length,
Of the stroke.
yep, length of the stroke, and you're going to love this, in feet. Just to be mean. I didn't make that up. Okay. Length of the stroke in feet. So if I had a 4-inch stroke a little bit ago, am I going to use 4-inch? No. Nope. I get 12 divided by 4. So yeah. So 3. Yeah, 3. Don't need a calculator for that. So length of stroke. So, okay. A. A is the area, which is the area of the piston. Area of the piston. In what? Inches squared. I know. N. N is the number. N is number. I don't know. Number of power strokes per minute. Power strokes per minute. Now let me ask you this: how, if my crankshaft went around just twice, how many power strokes did I have? I had 1. So it is also the same thing as saying RPM divided by 2, or 1/2 RPM. Because the number of power strokes per minute is half of the revolutions per minute. So if it went around, the crankshaft went around 1,000 times in 1 minute, how many power strokes did I have? I had 500. Okay. And K is the number of cylinders. You laugh at me, but now you won't forget that. It is the number of the cylinders. I just added the cylinders there. Maybe I should just spell it cylinders with a K. K-Y-L-I-N. Cylinders. I don't know.
How about pipe with a C?
I know, yeah. What's so bad?
Because that's not how you spell plank, so you can't. It's plunk, so it's the number of cylinders. So, sorry about that. It just is. All right, we have enough time for one example. So let's do an example. If I have a 6-cylinder engine. It's got a 5.25 inch bore. Is this the same thing we did a little bit ago? Bore with it is the 4-inch stroke. It is running at red line at 2,700 RPM. What else do I need up here? Pressure. Very good. It has an IMEP. What does that stand for? Indicated mean. I think it's effective pressure. Of 160 PSI, which stands for pounds per square inch. PSIG is
Pounds per square inch gauge.
PSI is Pepsi.
Oh.
Ah.
Just bring it around, guys.
Second time around, I
Still fell for it. I did that like less than a week ago. I don't know. All right, so my P equals PLA and K. I'm just going to work it here. P is 160. The length is 4 divided by 12 equals 3. Wait, no.
1/3.
Okay, 1/3. Like, that is not right. 0.33.
No, it's just.
Right? 4 inches is 1/3 of a foot. Okay, not 3 feet. Area equals pi times the radius squared, which is area equals is a big number. And we have one more thing to do. This all has to be divided by something.
33,000.
Why 33,000?
That's what you said.
Because that's how much work an English workhorse could do in 1 minute. So remember, we're doing horsepower. So I'm going to scroll up just a little bit so I can write a little bit more. So I come up with a number 9259272 divided by 33K equals 280.58 horsepower.
And just to think, somebody made that up because they needed to sell something.
And that guy's rich. So it was worth doing a little math,
He's
right?
dead.
That's true. So it doesn't matter. All right, everybody got 280.58? If you did, you can go home. If you didn't, I say if you did, you can go home a winner. If you didn't, you can go home with somebody who needs to practice a little bit more.
I know, we got sprinkled on my